Ma'am, shall we start, ma'am? Good afternoon, one and all present here on the second day of International FDP on recent trends in graph theory and mathematical modeling and its applications. I welcome you all for today's session. We have Mr. BAKKYARAJ THANGARASU as a speaker. I take this opportunity on behalf of management, principal, HOD, and faculty members of Mohamed Sathak AJ College of Engineering to welcome him. Welcome you, sir. Mathematical models are used in applied mathematics and in the natural sciences such as physics, biology, earth science, chemistry, and engineering disciplines such as computer science, electrical engineering, as well as in non-physical systems such as the social sciences. It is used to solve problems, to explain the system, the effective of different components, and to make prediction about behaviors. We are so happy to conduct 1 week FDP on such a significant topic for all the faculty members of engineering and technology across different countries. Hope this FDP program would provide in-depth exposure in this field. Now I invite Dr. Ammu Kodishya, HOD of Mathematics, for the welcome address.
Thank you, Sudha ma'am. Good afternoon all. This is Dr. A. Ammu Kodishya, HOD, HNS Department, Mohamed Sathak AJ College of Engineering. On behalf of the management, principal and staff, I take this opportunity to welcome our resource person, Dr. BAKKYARAJ THANGARASU, Assistant Professor and Head, Department of Computational Science and Humanities, Indian Institute of Information Technology, Kottayam and Kerala. I welcome you, sir, and thank you so much for accepting our invitation and being a resource person for today's session. We are so grateful to you, sir, and we are eagerly waiting for your session. And also, I welcome all the participants from other colleges who have shown great interest on this topic. I welcome you all, ma'am and sirs, and also I take this opportunity to welcome our coordinator, Mrs. S. Sudha, and N. Satya ma'am of our college. Without any further ado, let us move on to the session. Hope we all enjoyed this session. Over to Sudha ma'am. Thank you. Sudha ma'am.
Sudha, you are muted.
Okay, sir. Okay. Sorry, sir. So, once again, sir. After welcome address, we can start the session, sir.
Okay. Shall I start now?
No, sir. I have to give some introduction about you, sir, and then we can start.
Okay.
Okay, sir.
Sudha ma'am is eager to give you your introduction. She's very happy to introduce you, sir.
Yes, sir. Yes, ma'am. Because he's my friend now, so brief introduction I want to give about him. That's why.
Please carry on, ma'am.
Thank you, ma'am. Thank you. I take immense pleasure to introduce today's speaker for Day 2 of International FDP. My hearty welcome to Dr. BAKKYARAJ THANGARASU, Assistant Professor and Head, Department of Computational Science and Humanities, Indian Institute of Information Technology, Kottayam, Kerala. He received his doctorate in 2015 from University of Madras. His broad field of research is nonlinear differential equations. He also has 2 postdoctorate fellowships from University of Stuttgart, Germany, and the Institute of Mathematical Sciences, Chennai, India. To his credit, he has more than 12 plus publications in both national and international journals. He has also presented many papers in international and national conferences and acted as a resource person in various faculty development programs. Also, he has organized international conferences, webinars, and workshops. He has 14 plus years of teaching experience, and also he is one of the members in Indian Mathematical Society and reviewer in reputed international journal. Now I invite Dr. BAKKYARAJ THANGARASU, sir, to take over this session. Welcome you, sir. We can start the session now, sir.
Yeah, thank you, Sudha, for your nice words. And
thank you, sir.
I thank all the speakers and the head of the department for inviting me for this workshop. Talk in this workshop. Okay, so let me share. I already shared, so just a minute.
You already shared, sir.
Yeah, so now it is full screen visible, right?
Yes, sir.
Okay. So actually, I'm in full screen mode. If you have any question, you can ask me. Okay, I can't able to access that chat box. Okay, so this is the overview of my talk. So I would like to briefly introduce what is mathematical modeling, what is the challenges in it, and I will show you how we can model a certain phenomena as a differential equation as a modeling. So for that, I plan to take some problem, the very famous problem in the biology. So we will focus one or two particular models in the mathematical biology, and then we will I will try to introduce, if time permits, I will introduce the new notion, that is a fractional calculus and the basic fractional derivatives, and what is the modeling in the fractional derivative aspect as well. Okay, so this is my plan of the today talk. So first let us start with first mathematical modeling. Okay, so this is a very fundamental challenges of any science, physics, chemistry, economics, or whatever it may be, or any field of engineering. The main challenging is description and prediction. So description in the sense, whatever we observe certain phenomena, we have to describe what it is mathematically. So we have to make it precise, what that observed phenomena. Not only that, after that, what is its subsequent future behavior, how to predict its future behavior with we have only that initial conditions at our hand, right? So these are all the two quite interesting and as well as the challenging aspects of any field of science and engineering. Okay, so the mathematics is a tool, it will perfectly match these two to address these two challenges. Okay, so in the description as well as prediction. Okay, so we already familiar, is a concise language, is a very beautiful tool. We can useful, and we can make the description and explanation of phenomena in a very natural world. Okay, so here modeling refers the use of mathematics as a tool to explain and make predictions of natural phenomena. Okay, so mathematical biology means if you are modeling certain biological phenomena. Okay, so that is called mathematical biology. Okay, so here in the model world, we have trade-offs, right? So if you use a very simple mathematics, like if you use a linear differential equation or linear models, then you may end up with an unrealistic situation. But if you go to more close to the realistic situation, then you will get too many parameters going to appear in your model. Okay, so this is kind of trade-offs. Okay, so we have to predict as much as possible, then finally we end up a highly nonlinear system. Okay, so let us see how this the nonlinear system come to picture when once we go to the very close to the realistic situations. Okay, so in any modeling of any phenomena, there are certain things its effects is negligible. Okay, that we can leave it, but there are certain things affect the model, but we are not interested to predict the behavior of those things. Okay, so that things are called usually independent variables. Okay, and there are certain things affect the model, and we are very much interested to understand it, the behavior of that things. So that is called a dependent variable. Okay, so for example, if you drop ink in a bowl of water. Okay, so here you can easy to observe in a natural diffusion way, the concentration of the ink will start evolving, right? So it will with respect to time and also with respect to space, the space also over the time changes, the diffusion pattern is also changing. So here the space and time are two things that is we are not interested. What is our interest is the evaluation of the diffusion of the concentration of the ink, so that the density or the concentration of the ink is here we are interested to model. So that is called a dependent variable. and the time and space we are consider, that is independent variable. So the concentration C depends on X and T. Okay, so these are all the two things whenever we are modeling certain phenomena, we have to understand which things we are interested to predict. Okay. So we pretty much we are all familiar with the differential equation. It's just an algebraic equation involving function and its derivatives. Okay, so derivative is nothing but the rate of change of the function, given function. Okay, so this is the basic definition of a derivative, the limit of the difference, the quotient of differences. Okay, so when delta t tends to 0, then it will dn by dt. Okay, this is the rate of change. Okay, so now let us come to that modeling part. Okay, so here we are going to model the growth of microorganism. Okay, so first we are going to how to we represent or describe the model, and we after that we solve, and then we will get a prediction. So these two things. So first you have to model as an equation, and we solve that equation, and we can get the a subsequent future behaviors. Okay, so now let us start a very simple experiment. Okay, you take some amount of initial bacteria population, put it in a flask along with some nutrition food is also you added, and you kept the processes in a such a way that that environment will make the bacteria will eat the food and it will start growing. Okay, so here we have n naught initial bacteria. We start with the time 0, and then we allow them to evolve. The growth mechanism, microorganism will grow. Okay, so here the variable we are interested is the bacterial density observed at time t. Okay, so now we are let us start with this from now, this 2 p.m. This is my time t equal to 0. Okay, so now I want to know what is the, now I know the bacteria density at 2 p.m. That is my n naught. In the initial condition, n of 0 is n naught, some initial bacteria we put in that flask, right? So after an half an hour or after an day or often after a week, I want to know. So that is n of t. So if you substitute the t, whatever the time I want, so I want to predict how many bacteria will be available in that particular flask. That is my prediction. Okay, so here n is a dependent variable, the concentration or density of the bacteria, and t is the time. So for a simple model, I will restrict only time. Okay, I'm not bother about the space. Of course, there is a space variation is also there, but we don't want to make a more complicated model. So let us concentrate with only a single variable, so that we will end up with a ordinary differential equation. Okay, but you can generalize. You will make it as a PD. If you consider the variation over the space coordinates, then it will end up with a diffusion equation. That is a partial differential equation. Okay, for time being, let us. So here we fix a unit time. Okay, so the unit time means you can fix whatever. Say for example, you can fix hour or a day or a week or a month or a year. So that is up to us. Okay, so let us fix one unit of time. So here we can able to observe, okay, during the 1 unit of time, how many bacteria will be reproduced from the initial population. That we can able to measure. Suppose you assume that we have a sufficient facility to compute the number of bacteria present over the fixed unit time. Okay, it may be an as I said earlier, it may be an hour or whatever it may be, some unit time we fix. So that amount, that is we called is a parameter. Okay, so here k is the reproduction, the rate of reproduction over the unit time interval. Okay, whatever the unit time we fix, so in that unit time the k times the original bacteria will be reproduced. So that is the reproduction rate. So this is the parameter. Okay, so here we parameter we now we fixed as a constant. Okay, let us start with K is constant. Okay, over a per unit time, the new bacteria, K new bacteria cells will be produced. If you fix unit time is hour, every hour the new K number of new bacteria cell will be reproduced. Okay, so that is the parameter. Okay, so now we have a variable, dependent variable, independent variable, and a parameter. So with this, now we can model. So now I want to, so now n of t, I already told it represent the bacteria density at time t. Okay, so now I want to know what is the bacteria density at time t plus delta t. Okay, so that is nothing but, so at time t, this is the bacteria, and we need how many bacteria over the interval delta t. So that is K is the reproduction rate per unit time. So now we want delta T time, how many new bacteria produced. So that is, you have to multiply K into N over the period delta T. Okay. So K into N is per unit time. We want delta T time. So that is, you multiply delta T time. So this is the bacterial density at T plus delta T time. Okay, this is an approximation. Okay, because delta T is a very small time, therefore we can ruled out the higher order delta T square and so on, because it's just a Taylor series expansion. Okay, we keep only the linear term, right? So now we rearrange this equation. Okay, so in such a way that you bring this time and divided by delta t, you will get K times N of t. So now you will you allow that small delta t tends to 0, then this will become dn by dt equal to K times N. Okay, this is the Malthus equation. It's a very famous equation. If K is positive, this is called growth models. Suppose if your K is negative. So if K is negative means what it happens? What happens if K is negative? Any answer? What happens if K is negative? Yeah. See, K positive means every unit time we are added K new bacteria. Suppose K negative means we are removing. Okay, that is decay models. Okay, it's a decay model. Okay. Sorry. Okay. Anyway, so that depending on your parameter, if it is positive, it is a growth model. If K is negative, it is a decay model. Okay. So now if you solve this, it's a very simple linear equation. You can use the separation variable technique and apply the integration along with the initial condition n of 0 is n naught. Then we will get the solution. N of t is n naught into e to the power kt. Okay, so n naught is the initial population. There is an exponential growth. Okay, so as I said, if you're reversing the sign of k, then you will get continuously the k, the fraction k of individual will be removed from the population per unit time. Okay, so such as death or immigration to other environment. Okay, so this is the two solution. This is a growth model. This is the radioactive decay model. So this both the same model can applicable for radioactive decay also. Okay, so this is the solution. Do you feel this is the correct solution? Is a correct model for this? Do you identify any Is it a realistic solution or unrealistic solution? What do you think? Yeah, you can ask your question. What do you feel, whether it is a realistic model or unrealistic model? If you want, you can also chat. I can able to read. What do you feel? Is it a realistic model or unrealistic? Any idea? What is your opinion? So especially if you allow t tends to infinity. T tends to infinity means if you take a large time, what happens to the solution?
Becomes 0, sir.
No. You are talking about growth model, exponential growth.
Oh, sorry, sir.
Yeah, you are correct. If you consider decay model, it is going to 0.
You're going to 0, yes.
Yeah, I'm talking about the exponential growth model. If t tends to, because n naught is positive.
Yes, it is indefinitely increasing.
Yes, it tends to infinity, isn't it? Whether is it a realistic?
It seems like unreal.
Yeah.
Unrealistic.
Yeah. Why it is unrealistic? That means, what it means, n tends to infinity means we will have bacterial growth is infinite.
Infinite, yes, sir. Yes.
Right. Infinite. So, but here, when we start this experiment, what we put in addition to bacteria?
So I missed that session, sir.
Sorry, okay. Yeah.
Okay,
so actually, we put some nutrition, food.
Oh, okay, sir. Okay.
So once how the new bacteria will reproduce, so it will eat and it will grow, right?
It will grow.
So there is a limited food is available. Therefore, the infinite population is not possible.
Yes.
Right.
Okay, sir. Okay.
So,
Right.
So where is the mistake? Where we did mistake is we fixed k is constant, but k is not constant. Because over the time the k will vary because of limited availability of nutrition. Right?
Oh, yes, sir. Correct.
So now we are going to fine tuning. Okay, so k should not be a constant. That reproduction rate should not be a constant. It should be a function of time.
Yes.
Now we will do the modification and let us see what is happening. Thank you for your input. Yeah. Okay. So now that is the, this is a subsequent idea. You can find the doubling rate or the doubling time or half-life time. Okay, if you consider growth models, how much time it is required, so that the initial population will be double. So that is called doubling period. You just substitute. You need to find the delta t. Delta 2 such that it becomes 2 times n naught. Okay, so if you solve, because you already have n of t, you just substitute n of t equal to tau 2, then you will get this, and you solve it, you will get your tau 2. So the doubling period is log 2 by k in this particular model. So likewise, you can also find the half-life time if you consider the radial decade models. Okay, so this is the idea. Okay, so here, this is the one famous quote. You can just to read it. So if you take a single bacterium, okay, suppose if you allow them, it will grow like in uncontrolled growth, like in the previous model. If n tends to infinity as t tends to infinity, so how it is happened? So let us see here. A single bacterium, every 20 minutes it will divide into 2. Okay, so then the 2 will become 4, 4 will become 8, 8 will become 16, and so on. Okay, so the geometrically it will reproduce. So in a single day, if it is happen like this, okay, but it is not the case, right? because only the limited food supply, it is not possible. Suppose if you assume what happened in a one single day, a single cell of bacterium cell, it will produce a super colony that is equal in size and weight is equivalent to the planet Earth, entire planet Earth. So that is not a realistic. So what we observed is the K is not constant. So the reproduction rate also changes with the time. Okay, so now we are modified in the earlier K is constant. Now we put K is a function of T, and we get the solution N of T equal to N naught exponential 0 to T K ds. Okay, so now again we are going to fine tune this model. Okay, so again here the same problem will arise. Okay, so that we are going to rectify. Okay, so now the reproduction rate not only change with the time, it also depends on the concentration, the food concentration, isn't it? So if you have more food, then the reproduction rate will be more, right? It's a directly proportional to the availability of the concentration of food. Okay, so so that K you can represent as some kapha times C. Okay, so it's a directly proportional. Okay, so here and I'm going to introduce another parameter that is called alpha units. Okay, the alpha, the parameter alpha. This is a unit of nutrition or consumed in producing 1 unit of population increment. Okay, so this is the another parameter alpha. Okay, alpha units is required to produce 1 unit of population. Okay, so therefore here the that the food concentration, the change of concentration with respect to time, because dn by dt, the rate of change of population is increased. So when it alpha times, so therefore here I putting negative because the food concentration will decay if dn by dt will increase. That is what we put minus here. Okay, so now you combine dn by dt is k times n, but k is also you replace kapha times c. Now you combine these two. Now you can solve this, and you will get c of t is minus alpha. So if you solve this equation, you will get this one. Okay, so now you can resubstitute this c of t here. Okay, the original equation. So now I use integrate this second equation, you will get this c naught is this initial condition. Now you substitute the food concentration in this first equation. Here you will see that here up to this this is a linear equation. Yes or no? It's a linear equation. Now if you close to the more realistic situation, in the moment you substitute the value of c in this first differential equation, you will see that it will product term is coming to picture. Okay, so here c naught times n into n squared. Understand? So now you will get a nonlinear differential equation. Okay, so that means when you close to very near to the realistic situation, you always end up with a nonlinear differential equation. We have a very rich theory in maths to solve linear differential equation, but for nonlinear differential equation, we need it's a very quite challenging. There is no single technique which can be used to solve all type of nonlinear differential equation. We have to develop a different analytical techniques or numerical techniques. Many techniques are there. Okay, so here in this case we can easy to solve exactly this equation. So here your k is even what we understood here, your k, the reproduction rate is also depend on the density itself. Okay, that is what we here your k we can understood that it is also depend on n. So that is what we get the non-linearity here. Okay, so we can do the rearrangement of stems, and this model you can rewrite like this. This is called the logistic growth model. So you will get the solution will ended up like this. Okay, so here you will see that when t tends to infinity, you don't get large infinite growth. Okay, so this is a more realistic solution as far as this simple biological model is concerned. Okay, so this is the one modeling of biological phenomena. Okay, the next model, um, this is very famous, you all people familiar, I hope, the two pieces interaction model, or Lotra Voltra model, right? Let go Voltra model, or prey predator model. Okay, this is a very famous model. Let us spend some time on that. Okay, so Lotka Voltra equations. Okay, so here we have prey and predator. Okay, so say for example here the prey is the number of fish. Okay, so you have an environment. So in that environment, the prey predator interaction is always there. Okay, so f of t, let us denote the number of fish. S of t denote the number of sharks. Okay, so the shark is the predator and prey is fish. Okay, so now the rate of change of fish. Okay, how it happened? So it's depending on the rate of change of fish population is increased. uh, Here, if a is a birth rate, okay, so a is the parameter, denotes the birth rate of fish per unit time. Therefore a times f will add to the rate of change of f. Okay, then because it is in the same environment, whenever the fish meet the predator, that means whenever the shark meet the fish, then it will eat the fish. Therefore the fish population will reduce. Okay, how much at which rate it will reduce? It is the consumption rate of shark, depending on the consumption rate of the shark. So that is we denoted as p. So here I put minus because the fish population will decrease by the amount p times s comma f. So whenever the two entities are interaction, then we will write it that mathematically as a product of product. Okay, so here f and s times p. Okay, so once um, uh, shark eat fish, then automatically the shark population will increase. Okay, so that is here also that fs will meet, and this will added to the population of shark. Okay, and of course the natural the death rates of sharks are there, because once the fish population is decreasing and the shark population is increasing, then naturally uh, we scarcity of fish will come, then the shark will started to die. Okay, so that's a d is a death rate, so that is minus d times s. Okay, it's a very simple model. We have, if you can we assume many things so that we will get very simple, but if you add more constraints, if you consider more thing, then the more parameter will come and the model will complicated. But this model itself is a nonlinear coupled system. Okay, so this is the two pieces interaction model, and it's what's called modeling. Okay, differential equation modeling. And this is also another modeling. This is very famous, the classical SIR models. Okay, there are many variants, and a lot of people did research, especially during the last pandemic. Okay, and the corona modeling also, people will heavily used this classical SIR model. Okay, so here there are three type of people in the population. one people is called susceptible or healthy people, and infected people and recovered people. Okay, so these S plus I plus R, that is a total population, capital N, for example. So this will change with the time. Okay, so these all are depending on time. During the time it will so if one person, so here also we in the crab theoretical point of view also, you can think that it's a complete graph. Okay, so if one person is infected, it's a possibilities that he will meet all the person randomly. Okay, so it's a complete graph. So here the susceptible person, I mean the healthy person, if he meet the infected person, then um, with the rate of infection rate is R, then the population, the healthy population will decrease, right? So whenever S and I meet, then at the rate R, so the population will decrease. So likewise, once the infected person meet the healthy person, then the healthy person will become an infected person. Therefore, that will be added to the rate of change of infected person. Okay. Likewise, if we are giving some medication and the person will get recovered from the disease, then at the rate of recover rate is say for example A, then AI is the recovered population. So that is the dr by dt is AI, and here the same amount of infected person will be removed from the dA by dt. Okay, so this is a very basic SIR model. It is not only applicable for the analysis of communal diseases. The same model you can apply in the computer science application. For example, in the growth of internet, the very one of the biggest challenge is the cyber security. Okay, that means the computer virus. So the computer virus is nothing but it's a computer, some code, computer code. Okay, so if people are using it will come to social network, say for example we will receive some link in the mobile or email. If you click that link, then all of your personal informations or photos, videos in your mobile, that will be captured by a third person. Okay, so that is the spread of the computer virus. Okay, so the same model, you can use it for predicting the infection of computer virus in the social network. Okay, the same model, they're also susceptible, infected, recovered. Okay, the same model you can implement it in for the spreading, the controlling of computer virus in the and cyber security domain. Maybe here you can add some more new entity that is called exposed class. Also, you have to add it in addition to the SIRE, and there are certain probability also there, so that it will end delay differential equation modeling for that particular type of problems. Okay, so I'm not going to do that here. Just for your information, I mentioned here. Okay, so these are all the possible mathematical modeling. Okay, so now, yeah, so now we can slightly I would like to introduce the domain of fractional calculus. So whatever we discussed so far, they are all are integer order derivatives. Okay, the order of the derivative is integer, first order, second order, and so on. So now we are going to talk about the generalization of these classical derivatives. Okay, so that means we are going to talk about the non-integer order derivative of non-integer order derivatives. Okay, how do we generalize? So this is a little I hope some of you are already familiar with this fractional calculus. So just for giving an information if you are new to that. Okay, so these are the two famous mathematician. Leibniz, he introduced the calculus, right, from the geometric point of view. He treated derivative as a slope, okay, the tangent. Okay, so when the Lebanese introduced the notation for nth order derivative, dn y by dx power n, when n is a natural number. Okay, so then El Hospital asked the question, what this notation represent if n equal to half. Okay, that means he asked what is the half order derivative, what it means. Okay, so then Lebanese replied that this is an interesting question. So the useful consequences will be drawn. So from these words, mathematicians started to generalize this notion of differentiation. So this is our usual practice in mathematics, right? Whatever originally we are defining some operations for some set of objects, then we try to always extend to a bigger class of objects, right? So for example, x to the power n, when n represent a natural number, it means x multiplied with itself n times. Okay, you can easily generalize that n to be a set of real numbers. So that is x to the power n. You can write it as e to the power n times logarithmic of x. Using this generalization, we can define x to the power natural real number. Likewise, the factorial function, be familiar with that. If n is in natural number, you multiply 1 consecutively up to n. So now we can generalize to that positive real number. So through that gamma function. Okay, so through gamma function we can define the factorial. So gamma function is defined for all real numbers except negative integers. Okay, through analytic continuation. So likewise, the other generalization people started the nth order derivative when n is in n. So now we try to generalize the order of derivative could be a non-integer order. Okay, so in fact now we generalized the order could be a complex also. Okay, and even people also generalized the alpha is not only constant, it's also variable order. It's also a function of t. Okay, now in the literature people generalized the derivatives power is an variable order. Fractional derivative also developed people currently. Okay, yeah, so the fractional calculus, why this is fractional means because of the L Hospital asked the question. The first question is n equal to half, so that is why it is called fractional. But it is an calculus of non-integer order. Okay, dealing with the fractional, integral, and derivatives of non-integer order. So this is one famous quote lies between complete differentiation and integration. Okay, let me define fractional integral first, and then I defining fractional derivative, and I will show you some models, fractional derivative models. So why these fractional derivatives are important. Okay. So this is our Cauchy formula for n-fold integration. So if you integrate a function continuously, consecutively n times, you will end up with this 1 by n minus 1 factorial. So I told the factorial function can be replaced by gamma function. So n minus 1 factorial, you can write it as gamma n. Okay. So now this is an n is real natural number.
Hello, sir. Hello, sir. BAKKYARAJ, sir. Sir, you can unmute and mute again. Sir. You can unmute, sir.
Hello, am I audible?
Yes, sir. Now it's audible. Yes, sir.
Okay.
Thank you, sir. Carry on.
Okay. So now only it got unmuted, or I didn't see that.
Sir, now only.
Oh, okay, fine. Okay, so this is the nth order n-fold integration formula. So now I'm going to write what is the alpha order. Okay, if alpha is a positive real number, through this generalization, because I know a gamma function is defined for positive reals, therefore I can easily generalize this one. That is, we call it as Riemann-Liouville fractional integral operator of order alpha greater than 0 by simple observation of the using the generalization of factorial function and gamma function. Okay, so that is the alpha order fractional integral operator. Okay, alpha a to t minus alpha minus 1 f of s ds. Okay, just you replace alpha n by alpha and factorial by gamma function. That's all. Okay, it's very simple. This is the two name of the two mathematician. If you take a equal to 0, you will get a Riemann integral definition, and minus infinity to t, you will get Liouville. So we put a, so people will call the Riemann-Liouville fractional integral operator. So this is the one, the power function, the Riemann integral of a power function of order alpha. So here you substitute f of x equal to x minus a power beta. So here you can use this simple substitution, and you rewrite this integral. You will end up with this beta integrals. So using the beta integral definition, and this is the relationship using the relationship between beta integral and the gamma function, you will get this. So this is the fractional integral of power function. You will get this. Okay, so for any alpha, you can get the fractional integral of power function. So likewise here, fractional integrals possess all these classical integral operator properties like linearity, semigroup property, commutativity property, reciprocity property. All this property which is applicable for the classical integral operator can be carried over to fractional integrals. Okay, but that is not the case for fractional derivatives. So this is an one straight generalization of fractional derivative, like our quotients, right? So some question, is it fine? Okay, something different. Sorry. Okay, so this is the first derivative, and second derivative, third derivative, and so on. This is an nth derivative. We can represent in polynomial type the finite term sum. Okay, this is our classical nth order derivative of a function f. You can write it in this manner, right? So now what I'm going to do is that we can directly replace n by alpha. Okay, what is going to happen is this finite sum will become an infinite sum. Okay, so here you see that yeah, this is the numerator, the same thing. So now I'm going to replace the integer, the natural number n by the positive real number alpha. So in that case, what is going to happen is this finite sum will become an infinite sum, because this n choose r for a positive real number, it is non-zero. Okay, therefore you will end up with an infinite series. Okay, so here n choose r, if your r is greater than n, then it will become 0, right? Because it's a finite sum. But here, even if your r is bigger than alpha, also this is won't going to be 0. Okay, so that's what the infinite sum is come to picture whenever you replace n by positive real alpha. Okay, so this is the ground wall Letnikov fractional derivative, which is a straight generalization of classical differentiation. So people, those who are working in numerical analysis of fractional differential equation, they will concentrate this ground wall Letnikov fractional derivatives. Okay. Okay. So this is a very famous lemma. So this is a straightforward from our fundamental theorem of calculus. You can easy to prove that. So you take m and m, both are natural number, and m is bigger than n. Then we can write f, a function having a continuous nth derivative. You can rewrite like this. Okay, so just fundamental theorem of calculus application proof is very straightforward. So now using this lemma, we can define alpha order fractional derivative. Okay, so here I take my alpha is my positive real, and I take my m is the integer part of alpha plus 1. Okay, that is a positive integer. M is a positive integer. I'm going to define. Okay, so here I am replacing n by alpha. Okay, so that you will get following this lemma, you can define like this. Okay, m minus alpha. So here m minus alpha is a positive real number because alpha is a real number. So earlier we defined the positive the fractional integral of positive order. Therefore this is the Riemann-Liouville fractional integral of f of t. After that you can define take mth derivative, classical derivative, then you will get this. Okay, so this is called Riemann-Liouville fractional derivative. Okay, so here one important thing here, you have to discuss the classical derivative and fractional derivative. The drastic changes. This is a non-local operator because suppose if you want to evaluate fractional derivative of f at a particular value of t, say t naught, in the classical derivative means it is just if you know the value of f in the neighborhood of t naught. Okay, just f of t naught plus h minus f of t naught. That two values is sufficient to calculate f dash of t naught. But if you want to calculate fractional derivative of t naught, you required the entire interval from a to t naught. Okay, so you need a previous values of f from a to t naught. Okay, so this is called non-local operator. Okay, in order to estimate the fractional derivative of a particular time t naught, you need a full range of values for f of t. So this is called memory. It predicts the memory effect in the system. So whenever you have a system which has a memory effect, you can use the fractional derivative as an appropriate model to predict the memory dependent properties or memory dependent system. Modeling this fractional derivative will plays a very important role because of non-local operator. Okay, this is a drastic difference between classical derivative and fractional derivative. That classical derivatives are local. This is a non-local operator because the integral is involving. So likewise here the fractional derivative of power function. Okay, so this is, you can get it like this. So here if your lower limit is 0, if your lower limit is minus infinity, you will get like this classical result. So here let me show you some properties. So let us take your f of x is root x. So now you take what is the half order derivative of root x. So in this formula, lambda equal to half and alpha is also half. You simply substitute here. You will get using the gamma of half is root pi, and you will end up root pi by 2. This is the half order fractional derivative of root x. Likewise, 3 by 2 order of root x, the same thing, alpha you substitute 3 by 2, lambda is equal to half, and here you will get gamma 0. So gamma 0 is infinity, 1 over infinity will become 0. Okay, so now you swap it. First you apply 3/2 fractional derivative of root x, and then you take half order derivative, so you will get 0. But if you make a commutative, first half order and then take 3/2 fractional derivative, then you will end up with this function. So what you observe is that the fractional derivatives are not commutative. You understand? And of course, they are not satisfying the semi-group property. That means d alpha d beta of f is not equal to d alpha plus beta f. Understand? So the first derivative of root x is not same as of this one. The semi-group property is violated and the commutative property is gone. You understand? And there are, say for example, fractional derivative of a constant, it is not 0. And the Riemann-Liouville fractional derivative is concerned, it is not 0, because here if you take lambda equal to 0, then it will become 1. If you substitute lambda equal to 0, you won't get 0. You will get x to the power minus alpha by 1 minus alpha, gamma 1 minus alpha. It is not a 0. So this is the limitations of Riemann-Liouville fractional derivative. There are many stuff, and also here, when you try to solve fractional differential equation using transform technique, so here this is the Laplace transform of Riemann-Liouville fractional derivative. Okay, so here you see that the initial conditions involving a fractional derivative. So here I would like to stress one more thing. The physical meaning of fractional derivative is still now we are not clear. Okay, say for example, first derivative, classical first derivative is velocity, second derivative is acceleration, and so on. The physical meaning is there, but alpha order fractional derivative, we don't have any such kind of physical or geometrical interpretation as of now. Okay, so therefore the initial condition involving a fractional derivative, it doesn't have a physical meaning. Okay, so these are all the drawbacks of Riemann-Liouville fractional derivative is concerned. Okay, but I would like to stress that point also. So here you see that if you want to take a derivative of a function, it should be continuously differentiable. Then only you can able to take a derivative, right? Basically, it should be a continuous function. Then only you can take a derivative in the classical. Suppose you have a function like Weierstrass function, say for example, it is nowhere differentiable, right? So in those function, you can take a fractional derivative, because first we are taking an integration. So the integration is a smoothing operator. So after that you can take a derivative. Okay, so if you have a non-differentiable function, you can take a fractional derivative. That is the advantage of Riemann-Liouville fractional. But physically, these are all the disadvantage I mentioned in the lack of physical interpretation of fractional derivatives. So in order to overcome that, people introduced a Caputo fractional derivative. Just a swap of first you differentiate, after that you take a fractional integral. That's all. So here you see that if you f is a constant, because you first take a derivative, therefore it becomes 0. So the Caputo fractional derivative a constant is 0. And the second issue is if you take a Laplace transform of Caputo, here you will get our integer order initial, the derivatives, integer order derivatives, so that initial condition have a physical interpretation, so that it can be used, because it swapped, right, the fractional power to that factor, and initial conditions are in the classical derivatives. So this is the advantage of Caputo fractional derivative. So I will stop here, because is it okay? Okay, anyway, let me stop here. Yeah, it's time is up.
Okay, sure.
Yeah.
Dear participants, if you have any doubt, means you can ask our resource person.
Yeah.
Dear participants, if you have any doubt, means you can ask to resource person.
Yeah, you can unmute yourself and you can ask.
Or otherwise, you can put into the chat box.
And one more thing, in the fractional calculus, the derivative is concerned, the standard product rule, standard chain rule, that are not available for fractional derivatives. That means d alpha of fg, you cannot write like d alpha f times g plus f times d alpha g. Okay, the classical product rule or a chain rule, they are limitations of fractional derivatives. But uh, these non-standard properties will help us in another aspect. So it will predict a non-standard processes like anomalous diffusion. Okay, the anomalous diffusion is the slow movement of particles and the fast movement of particles. Those kind of non-standard properties or physical system we can model using this fractional derivatives. That is an advantage of fractional derivatives. Okay, you can think there are certain limitation, but the limitation will give you a certain other aspects. That's the beauty of this fractional derivatives.
And dear participants, if you have any doubt, kindly interact with our resource person.
Yeah, of course, Dr. Srilashmi, you can use it because there are many models. People try to, yeah, of course, as far as mathematical analysis is concerned, many people started replacing the classical models by the fractional derivative, and they will look for the solution or any efficiency, any stuff. Even if you take computer algorithms are concerned, there are many algorithms based on gradient based algorithms are there, and people now started to use the fractional calculus, fractional derivatives in the gradient based algorithms, and they are started look at for the efficiency of the modeling. Okay, so yeah, it is possible. So only thing, what I'm in general principle, what I'm saying, if you have a system which has a memory dependent properties, it's highly recommend you can use fraction order derivative models instead of classical derivatives. Okay, that is very interesting stuff. Let me, if you can, I take 2 more minutes just showing one fractional derivative model, Sudha.
Yes,
Is
sir.
it,
Sure, sir.
okay, only 2 minutes. I will stop because people asked, because you will feel why this fractional derivative occur naturally. Just I will show you that and then I will stop. Okay.
No issues, sir. You can
Okay.
carry on.
Okay. So here, let me show you this model and then I stop. So this is viscoelastic material. There are certain material in physics, material science. Okay, so here we need to talk about the stress strain relationship of viscoelastic material. Okay, so there is a physics rule, that is Hooke's law, is available for pure elastic solids. The Hooke's law will give you a stress strain relationship for pure elastic solids. So this is the stress strain relationship for pure elastic solid. So I'm going to rewrite this for the sake of illustration. It's an integer order identity operator. Sorry, identity operator. You can get it the same thing. Okay. Likewise, if you consider a pure viscous liquids, the stress strain relationship for pure viscous liquids is described by using our Newton's law. So this is the Newton's law for the stress strain relationship for viscous liquids. Okay, so now we are getting some material, as I mentioned, viscoelastic material. Okay, so this is a particular type of materials, okay, which exhibits a behavior somewhere between pure elastic and pure viscous. Okay, it's an intermediate property these viscoelastic material possess. So now for this type of material, the stress strain relationship for viscoelastic material, the people started using the fractional derivative models. Say for example, this is a very basic model, and there are a lot of generalization for this viscoelastic material. Right now, people generalized. So the idea is this is the because in the classical model, the classical derivatives. So now I'm going to replace the classical derivative by fractional derivative, so that this model will predict very realistic for the viscoelastic, as far as the stress strain relationship is concerned for viscoelastic material. Okay, so here also when alpha, the parameter, the order of the fractional derivative tends to 0, you will get the Hooke's law. Okay, because alpha 0, then you will get the Hooke's law. When alpha goes to the other extreme, pure viscous, then you will get back your Newton's law. So this is naturally this fractional order model is arising in the this stress strain relationship is concerned. Okay, that one more model quickly I explain. This is called our one-dimensional heat or diffusion equation. Okay, the fundamental idea of heat equation is the mean square displacement is on linear on time. Okay, directly proportional linear. So here the t equal to 1. Okay, so there are certain process I mentioned earlier, non-standard process does not obey this classical rule. Okay, so that means that non-standard process, what I mean is anomalous diffusion. Okay, so the mean square displacement is directly proportional to t to the power alpha. It will connect it non-linearly, not alpha equal to 1. So these kind of anomalous diffusion we can model through the fractional diffusion equation or fractional heat equation. Okay, so if your alpha is lies between 0 to 1, that is called subdiffusion behavior. I mean the slow movement of particle. When alpha is greater than 1, that is called super diffusion, the fast movement of particles. You can predict using these models. Okay, so this is what I would like to say, these two fractional derivative models. Okay, yeah, that's all. Yeah, any other question? Fine. So if you have any questions, you can write to me, BAKKYARAJ at Kottayam ac.in. Okay, to mail also. Okay.
Dear participants, any other queries? Okay, sir.
Okay, thank you.
Thank you so much, sir.
Okay.
Now I call upon Dr. Satya ma'am, Assistant Professor Mathematics, to deliver the vote of thanks.
Good evening, ma'am. Can you hear my voice?
Yes, ma'am. Yes, ma'am. Carry on.
Okay. Good evening, sir. Good evening, honored all gathered here on this wonderful evening. I would like to present the vote of thanks. It has been such an honor to be part of wonderful event. On behalf of the organization, I would like to extend my heartfelt gratitude to our esteemed guest, Dr. BAKKYARAJ THANGARASU. This FTB was really nice. You motivated us gain more and more knowledge in our respective field. Thank you, sir. Next, I would like to our beloved principal and head academic sir, HOD ma'am, all staff members, participants and volunteers. Last but not least, our beloved audience for making this FTB as a grand success. Once again, I thank one and all present here. Thank you.
Thank you, ma'am.
Thank you, Sudha. Bye bye.
Thank you, sir. Okay, sir. I will call you, sir. Thank you.
Okay. Bye bye.
Thank you,
Thank
sir.
you,
Bye.
sir.
Dear participants, kindly fill the feedback form. It is considered to be your presence with feedback. Thank you all once again. Kindly fill the feedback form. Thank you all once again.